This is a video summarising all of the content in the second organic chemistry topic in AQA A-level Chemistry. In it we cover alkanes, fractional distillation, cracking, combustion and chlorination of alkanes. This video might be useful in preparing for an end of topic test or even AS or A-level paper 2. In GCSE chemistry you learnt that alkanes are saturated hydrocarbons. You should know that a hydrocarbon is a molecule or compound that only contains carbon and hydrogen atoms with nothing else. Saturated means that all of the bonds between these carbon atoms are single bonds. Those single bonds are not able to rotate, and this means that alkanes do not exhibit EZ isomerism. Each of the carbon atoms in an alkane has a tetrahedral shape around it, and this is because each one of those carbon atoms has 4 bonding pairs of electrons, and these are going to equally repel each other and therefore try to push apart to be as far apart as possible, and this will give a bond angle of approximately 109.5 degrees. The molecule is nonpolar because the bonds are relatively nonpolar, and this is because there is similar electronegativity from both hydrogen and carbon. You should know that larger alkanes have higher boiling points due to the stronger van der Waals forces between the molecules, which require more energy to overcome. Branched alkanes have lower boiling points than unbranched alkanes, and we can explain this by thinking about how they pack together. So unbranched alkanes can pack together very easily, and the weak intermolecular forces between them are comparatively strong. However, if I draw an isomer that includes a branched chain, this branching prevents those alkanes from packing together so well. And this means that the weak intermolecular forces, the van der Waals forces, are weaker, and this reduces the boiling point. To name unbranched alkanes, we're going to use the exact same system that we used at GCSE. So we have a prefix which is determined by the number of carbons, so meth, eth, prop, bute, pent, hex, and then we're into our shape names, and then we put ane on the end of that as a suffix. But we can also use the same system for naming rings. So if we've got, say, a carbon ring with 6 carbons in, then that will be cyclohexane. Crude oil or petroleum, which is not the same thing as petrol, is an unrefined fossil fuel. It's a finite resource found trapped within rocks, and it's formed from the remains of ancient biomass, as creatures died millions of years ago and their bodies were buried in sediment and exposed to high temperature and high pressure over millions of years and slowly broke down. Crude oil is a mixture of hydrocarbons, mainly of the alkane class, and these different alkanes are used as fuels and chemical feedstocks, and we use a process called fractional distillation to separate the different hydrocarbons so that they can be used. Fractional distillation is used to separate mixtures of compounds that have similar boiling points, and in the case of alkanes that's going to be because they have similar chain lengths. We use a fractionating column, and at the start of that fractionating column there is a furnace which is heated up to about 350 degrees C, and the unrefined crude oil is pumped in through a pipe that passes over the top of that furnace so that the crude oil is being heated. The vast majority of those hydrocarbons, those alkanes, will evaporate and they'll go up the fractionating column. But some very, very large alkanes are extracted as liquid because even 350 degrees is not hot enough to evaporate them, and that's what we call residue. The remainder of the alkanes which have evaporated carry on moving up the fractionating column, which has a temperature gradient. So it's very hot at the bottom, but at the top it might only be about 40 degrees C. And so as the different alkanes move up this column, they cool, and as they reach their individual boiling point, they condense and can be extracted, and they'll form a fraction. So as we're moving up the fractionating column, we're producing not individual compounds, but groups of compounds that have become a liquid at the same point because they have similar boiling points. So the molecules that are being collected at the very top are the smallest molecules. They have the lowest boiling points. They have low viscosity, so low stickiness, and they're also highly flammable, so they make the best fuels. There's greater demand for the petrol and diesel fractions than can be supplied from crude oil alone, while larger fractions like fuel oil are more available than necessary. Cracking is a process that allows this surplus of fuel oil and other large fractions to be converted into smaller, more useful molecules. In GCSE chemistry, you learnt that cracking was a type of thermal decomposition, so it's using heat energy to break apart molecules, and that in that process carbon-carbon bonds were broken. Conservation of matter means that the number and type of atoms cannot change during a chemical reaction. So when we break apart a large alkane like this decane molecule, if we make an alkane like this octane molecule, there's not enough hydrogen atoms left over to make a second alkane. So we can't make another one, so instead we make this ethene, which is an alkene. Whereas at GCSE we would have said that cracking had to produce an alkane and an alkene, in Year 12 chemistry we explore some other options. Here we've got that same decane molecule and we break it apart to make butane, leaving 6 carbon atoms and 12 hydrogen atoms. I could make hexene, but the other thing I can do is to make a cyclical molecule, which is cyclohexane. So we can revise our GCSE understanding to say that we're going to make a smaller alkane, but then there are a number of other options, including unsaturated alkenes, but also cyclical hydrocarbons that are saturated. Having used a simple prefix and suffix to name alkenes at GCSE, in Year 12 we moved on to say that actually it's important where the double bond lies. So we have but-1-ene and but-2-ene, but don't forget that this is still but-1-ene because we're always counting from whichever end of the molecule is going to give us the smallest number. And then we also have to remember that this molecule is just propene because there's only one possible location for the double bond. As you learnt at GCSE, we can test for the presence of unsaturated bonds by using bromine water. So bromine water is orange and it remains orange in the presence of alkanes or cycloalkanes as well, but it turns colourless when in the presence of a double or triple bond. So now for the frustrating bit. And I'm going to preface this by saying that although at GCSE we learn about 2 types of cracking and at A-level we learn about 2 types of cracking, actually there are loads of different types of cracking. And the particular type you're doing and the reaction conditions you're using are dependent on the product that you're particularly interested in making. So are you wanting alkenes for making plastics? Are you wanting aromatic hydrocarbons? What is it you're trying to achieve? So the irony is that at GCSE we kind of mixed and matched some different types, and you'll see what I mean in a second. But I would strongly suggest that you just put everything you know about reaction conditions for cracking from GCSE to one side and start from scratch. So our first type of cracking, and this is the one that we did talk about at GCSE, is catalytic cracking. So catalytic cracking, technically speaking, does involve slightly elevated pressure. So atmospheric pressure in the room with you right now is about 100 kilopascals. Industrially, they're going to use about 200 kilopascals, so about 2 times the normal atmospheric pressure. So we can kind of fake it in a GCSE school lab, but it doesn't work as well as it works if it's got slightly increased pressure. It uses a reasonably high temperature, so 600 degrees Kelvin, that's about 330 degrees C. You can definitely achieve that with a Bunsen burner. And we use something called a zeolite catalyst, so that's aluminosilicate or aluminium oxide. That is the catalyst that you would have used if you did this practical at GCSE. You just probably wouldn't have been told that, but you now do need to know that name, zeolite. And ironically, given that at GCSE we told you that cracking was going to produce alkenes, catalytic cracking tends not to. It mainly tends to produce the motor fuels, so those are our short alkanes, and aromatic hydrocarbons, so those are the ring-shaped hydrocarbons. And then the second type of cracking that you need to know about is thermal cracking, which we didn't cover at GCSE. And that might be a bit of a confusing statement because you're thinking, hang on, but we said that cracking was thermal decomposition, so surely that is what it is. But the cracking that you did at GCSE, whether it was with a zeolite catalyst or with steam, that was all catalytic cracking. And the reason I know that it wasn't thermal cracking is that I guarantee you that you could not produce a pressure of 70 atmospheres in your school laboratory. You're just not going to be able to do it. So thermal cracking, when it's done in the industry, has this really high pressure. It's about 70 times higher than atmospheric pressure, and also a high temperature. So from slightly higher than catalytic cracking right the way up to about 1200 degrees Kelvin, which is way hotter than you could produce in your school laboratory. And thermal cracking is going to produce a high percentage of alkenes, so that's very useful if you're trying to make plastics, and also sometimes some hydrogen. Combustion means burning a fuel in oxygen, and one of the primary uses of alkanes is burning them as fuels. Combustion can be complete if it occurs in an excess of oxygen, and that means it's going to produce carbon dioxide and water as all of the fuel is fully oxidised. However, if there's insufficient oxygen available, then incomplete combustion will take place, and this would produce carbon monoxide or carbon particulates in addition to water. You also need to know about the atmospheric pollutants that are produced when hydrocarbon fuels are combusted. So there are various pollutants, and as you know, if we have complete combustion, we release carbon dioxide and water, and carbon dioxide leads to global warming. You already learned at GCSE that without greenhouse gases, the Earth would actually be uninhabitable because it's far too cold. Having greenhouse gases at small concentrations in the atmosphere maintains a temperature that is high enough for life to survive. You also would have learned that carbon dioxide, methane and water vapour were all examples of greenhouse gases. Sadly, we do need slightly more detail than this for A-level. So the first thing that we're going to say is that that upper layer of the atmosphere where we find these greenhouse gases is called the stratosphere. So here's my stratosphere, and in that blanket I've got carbon dioxide and methane and water vapour. As you know, short wavelength waves can penetrate through that stratosphere and reach the Earth. And then when they do, they warm up the Earth and then they're re-emitted as lower energy waves, usually with a slightly longer wavelength. So we're thinking infrared. And these are going to move up and they're going to interact with that stratosphere. Now the bonds in the greenhouse gases are going to vibrate. And the reason that they're able to do this is that they're slightly polar. So for instance here in carbon dioxide, we've got a slightly positive carbon atom, and then the more electronegative oxygen atoms are slightly negative. And this leads these bonds to start vibrating. So after this bond has been made to vibrate by absorbing infrared radiation, it then emits it again, and when it does so, it emits that radiation in all directions at once. So gradually this is going to warm up the atmosphere and warm up the Earth. You should also be able to describe enthalpies of reaction for combustion. The negative enthalpy value here for the combustion of nonane tells me that that reaction is exothermic. If we compare that to the value for methane, we can see that we've got a less exothermic value because smaller alkanes are less energy dense. If there's insufficient oxygen for complete combustion, then we could instead produce carbon monoxide, which is a colourless, odourless toxic gas that irreversibly binds to the haemoglobin in your red blood cells. Or we might produce carbon particulates, and also other kinds of particulates made from unburned hydrocarbons. These cause a phenomenon called global dimming, and this means that there are tiny particles in the atmosphere reflecting the sun's light back, so not as much sunlight reaches the ground. Almost all fossil fuels and the products that are made from them contain small amounts of sulphur as impurities. So when you burn the petrol or diesel, then you also burn the sulphur and make sulphur dioxide, and this is one of the contributing factors to acid rain, because as it dissolves in water in clouds, it produces sulphurous acid. Acid rain is also caused by carbon dioxide dissolving in that water and also oxides of nitrogen, which are produced in combustion engines when the very high temperature allows unreactive nitrogen to react with oxygen from the atmosphere. These oxides of nitrogen contribute to acid rain, but they also cause respiratory problems, and also at ground level they react to form ozone. All modern vehicles now contain catalytic converters in order to reduce the harmful emissions coming from the exhaust pipe. Modern catalytic converters consist of a support or honeycomb structure made from ceramic, and this provides a wide surface area which can then be sprayed or painted with a paste that contains tiny microparticles of metals like platinum or rhodium. These have a very high catalytic activity and allow the gases to be broken down into less harmful products. So within a typical catalytic converter, a platinum rhodium catalyst will be used to reduce nitrogen monoxide to make nitrogen gas and oxygen. And in the same catalytic converter, a platinum palladium catalyst oxidizes carbon monoxide to make carbon dioxide. Obviously, this isn't a particularly good thing for the environment, but it does make it safer for people living in cities. However, it's not just motor vehicles that produce emissions that are harmful to the atmosphere. Flue gases are produced from fossil fuel power stations as they're burning oil or coal in order to generate electricity. And just like the fuels for cars, they can also contain sulphur emissions and therefore produce sulphur dioxide. As we described earlier, sulphur dioxide will dissolve in clouds to form sulphurous acid and ultimately acid rain. In order to prevent this, within the power station, calcium oxide or calcium carbonate are used to carry out an acid-base reaction and remove that sulphur. So typically, calcium carbonate would react with sulphur dioxide to produce calcium sulfite and also carbon monoxide. However, if additional oxygen is added, then we can make calcium sulfate and carbon dioxide. Alternatively, calcium oxide can react with sulfur dioxide and some oxygen to just make calcium sulfate without producing any carbon dioxide at all. These two reactions are possible because sulfur dioxide is an acidic gas and calcium oxide and calcium carbonate are both basic. A free radical is a species that has at least one unpaired electron in its highest energy level, making it unstable, short-lived and highly reactive. We represent the unpaired electron using a single dot. The classic example of chlorination is the reaction of methane with chlorine, and depending on which of the reactants is in excess, we're going to make slightly different products. So here's methane, which you're very familiar with, and we could make chloromethane, which is just methane with a single substituent group where chlorine has replaced hydrogen. And that's what will happen if the methane is in excess. But if the chlorine's in excess, then it's possible for multiple substitutions to happen, all the way up to tetrachloromethane. So tetra means 4, like a tetrahedron, and therefore this is methane that has 4 chlorine groups. The mechanism for this reaction is free radical substitution. In other words, that species with the unpaired electron is going to come in and take the place of one of the hydrogens in this methane. So there are 3 parts to this reaction. There are going to be slightly more than 3 equations, but basically we're breaking the whole reaction down into 3 bits. So the first part is called initiation. Initiation means starting the thing going. So we're going to make some free radicals. And the way that that happens is that some chlorine molecules are going to break apart homolytically. So that means that both of the atoms in the bond are taking the same number of electrons. So they're both going to get 1 electron from that single covalent bond, and therefore they're actually going to be free radicals. They're going to have this unpaired electron. Now, in order for that to happen, we need some UV light, and this is going to provide the energy to break that covalent bond in the chlorine molecule to form these chlorine free radicals. Now, this isn't going to happen to every single molecule. Some of the chlorine will not react and it will stay as chlorine molecules, but some of it will break down to make these free radicals. The next step is called propagation, and this is actually going to have 2 different equations that we need to know. You might have heard the word propagation outside of chemistry, either in gardening, where we talk about propagating plants when you're making new little plants and spreading them out, or in terms of an idea being propagated if you share it with someone else and it kind of goes on and goes further and further. Because this reaction is not just one and done, it can continue happening and continue happening until eventually the termination happens. So there are 2 parts to it. In the first part of the propagation reaction, a methane molecule is going to react with the chlorine free radical. And basically that chlorine free radical is going to pick up a hydrogen, and we're going to be left with a methyl free radical. So it's methyl rather than methane. We've ripped off a hydrogen which has taken an electron with it. So we've basically put together a hydrogen free radical and a chlorine free radical to make hydrogen chloride, and we're left with this methyl free radical. But of course that methyl free radical is also really reactive, and so what's then going to happen is that methyl free radical is going to go on and attack another chlorine molecule, and so this is where we get our chloromethane, and then we have regenerated that chlorine free radical, so the whole process can start again. So finally we've got termination, and termination is the end of the reaction. So basically it's going to happen when 2 different free radicals join together to make a neutral molecule where all of the electrons are paired. So we've got 2 different free radicals in this reaction so far. We've got the chlorine free radical and we've got the methyl free radical, and they can join up in any pair in order to terminate the reaction. So we could have a chlorine free radical and a chlorine free radical joining back together to make a chlorine molecule in kind of the reverse of that initiation step. But we could also have 2 methyl free radicals joining up to make an ethane molecule. Or if we had a chlorine free radical and a methyl free radical joining up, we could also make chloromethane in that way. Thank you very much for watching, and I hope you're now feeling more confident about this second topic in organic chemistry. If you're not, then remember the individual videos in this series have a bit more detail and also practice questions included. If you did find this video useful, then don't forget to like, subscribe, comment and share.